How it works. Weapons. The Glock revolution. The polymer frame sits on the inspection table like a challenge to 70 years of gunsmithing tradition. Its surface bears the subtle texture of injection molding, free from the machining marks that characterize every service pistol in the Austrian Ministry of Defence's current inventory. Weighing just 8 ounces compared to the 2-pound steel frames of competing designs, it appears almost toy-like to the procurement officials examining it in the Deutsche Wagram facility this autumn morning in 1982. Colonel Weber hefts the prototype, his expression betraying skepticism that borders on dismissal. Traditional pistol frames require forging, machining, and heat treatment, processes that have defined quality firearms manufacturing since the Industrial Revolution. The object in his hands emerged from the same type of injection molding press used to manufacture automotive dashboards and appliance housings. No gunsmith's tools touched its construction, no hand-fitting adjusted its tolerances, yet the technical specifications challenge every assumption about materials engineering in firearms design. The polymer, a glass-filled nylon designated as polymer 2, withstands temperatures from -40 to 200 degrees Fahrenheit without dimensional change. Steel reinforcement inserts positioned at critical stress points create mechanical bonds stronger than traditional welded joints. The trigger guard integrates seamlessly with the frame structure, eliminating a failure point that has plagued military sidearms for decades. Gaston Glock observes the inspection from across the room, his background in advanced polymer chemistry providing perspective that traditional gunmakers lack. Where they see plastic, he recognizes a material that absorbs impact energy rather than transmitting it through the weapon's structure. Where they perceive cheapness, he understands manufacturing precision achievable only through automated processes. The contradiction runs deeper than materials. It challenges the fundamental relationship between craftsmanship and performance that has defined the firearms industry since its inception. The Austrian military specification demands seem almost contradictory: increased reliability, reduced weight, lower manufacturing costs, and enhanced durability under extreme conditions. Traditional approaches, better steel, tighter tolerances, more complex mechanisms, address individual requirements while compromising others. Glock's solution questions whether the conventional wisdom about pistol construction serves engineering necessity or merely industrial tradition. If stories like this help you see how engineering quietly shaped history, tell us in the comments what surprised you so far, and stay with us for the next chapter. Gaston Glock never intended to revolutionize firearms design. His company specialized in military equipment, field knives, entrenching tools, and casing components, products that leveraged his expertise in advanced materials and manufacturing processes. When the Austrian Ministry of Defense issued their pistol specification in 1980, established gunmakers like Steyr-Mannlicher dismissed the contract as routine procurement, confident that their decades of experience provided insurmountable advantages over an engineer who had never designed a firearm. This inexperience proved to be Glock's greatest asset. Traditional gunmakers approached the specification by refining existing designs, improving metallurgy, adjusting spring tensions, modifying extraction systems. Their solutions carried the accumulated weight of historical compromises, design decisions made for manufacturing limitations that no longer applied. Glock approached the challenge with the systematic methodology of a materials engineer, questioning every component's necessity and examining each manufacturing process for optimization potential. His background in polymer chemistry revealed opportunities invisible to conventional thinking. Advanced thermoplastics could replace steel in non-critical applications while providing superior performance characteristics. Injection molding achieved dimensional tolerances that manual machining struggled to match economically. Automated production eliminated human error while reducing labor costs by orders of magnitude. But these insights required abandoning aesthetic preferences that had guided firearms design for generations. The Austrian military's urgency stemmed from NATO standardization requirements and budget constraints that made incremental improvements insufficient. They needed dramatic cost reductions without performance compromises, exactly the type of challenge that favored innovative materials engineering over traditional craftsmanship. Procurement officials privately acknowledged that domestic political pressure demanded an Austrian solution, creating opportunities for companies willing to challenge established industry leaders. Glock's team included metallurgists, polymer specialists, and production engineers drawn from automotive and aerospace industries rather than traditional gun makers. Their perspective emphasized manufacturing efficiency and materials optimization over the hand-fitted precision that characterized premium firearms. This industrial approach horrified purists, but aligned perfectly with military procurement priorities: reliability, affordability, and consistent quality across high-volume production runs. The first prototypes emerged from Glock's facility in early 1982, incorporating design principles that seemed almost heretical to traditional gun makers. Simplified internal mechanisms reduced part counts dramatically. Polymer construction eliminated corrosion concerns while providing superior impact resistance. Manufacturing processes prioritized dimensional consistency over surface finish aesthetics. Every decision challenged conventional wisdom about what constituted quality in firearms engineering. The Glock operates on a modified Browning short recoil system, but its revolutionary elements extend far beyond mechanical action into fundamental materials engineering. When the trigger is pulled, 3 independent safety mechanisms must disengage in precise sequence. The firing pin safety releases, the trigger safety depresses, and the drop safety disengages. Only then does the striker move forward under spring tension to engage the cartridge, a trinity of protection that operates through mechanical logic rather than electronic complexity. Gas pressure from the burning propellant drives the projectile down the hexagonally rifled barrel while simultaneously pushing the slide rearward against the recoil spring's compression. The barrel tilts downward through a cam arrangement, unlocking from the slide, which continues its rearward travel to extract and eject the spent casing. The compressed recoil spring then drives the slide forward, stripping a fresh cartridge from the magazine and returning the barrel to battery position. This cycle repeats with mechanical precision, limited only by ammunition supply and component wear. The true innovation lies in the frame construction philosophy. Traditional pistol frames function as rigid platforms, transmitting energy directly to the shooter's grip. Glock's polymer frame absorbs impact energy through controlled flexion, reducing felt recoil while maintaining structural integrity. The glass-filled nylon material provides specific strength characteristics impossible to achieve with steel. High-impact resistance combined with dimensional stability across extreme temperature ranges. Manufacturing integration reveals the design's deeper sophistication. Steel reinforcement inserts are positioned precisely within the injection molding dies, allowing polymer to flow around them during the molding process. This creates mechanical bonds at the molecular level, stronger than welded joints and eliminating traditional assembly requirements. Surface texturing for grip enhancement is molded directly into the frame, not machined afterward. The trigger guard becomes an integral structural element rather than a separate component requiring fitting. Austrian military evaluators initially questioned whether polymer construction could withstand service conditions that routinely damage steel-framed weapons. Their skepticism reflected decades of experience with metal fatigue, stress fractures, and dimensional changes under repeated use. But accelerated aging tests revealed unexpected results. The polymer frames emerged from conditions that cracked traditional steel frames, their dimensions unchanged and their mechanical properties uncompromised. The resistance came not from performance deficiencies, but from institutional inertia. Military procurement traditionally equated weapon quality with weight, complexity, and expensive materials. The Glock challenged these assumptions with aggressive simplification: 34 total components compared to 70 or more in conventional designs, field strippable without tools, and manufactured through processes that eliminated hand-fitting requirements entirely. Do you think this design choice was inevitable or a risky gamble at the time? Share your view in the comments and pass this story to someone who enjoys understanding how things really work. The Deutsche Wagram test facility echoes with the methodical percussion of durability testing as technicians subject Glock prototypes to accelerated aging protocols that would compromise conventional firearms. Temperature cycling chambers alternate between Arctic cold and desert heat every 30 minutes, simulating years of environmental exposure in compressed timeframes. Drop tests from increasing heights measure impact resistance, while vibration tables replicate the mechanical stress of armored vehicle transport across rough terrain. Each failure provides data that drives immediate design refinement. Early prototypes reveal stress concentration points where polymer thickness requires adjustment. Temperature cycling exposes differential expansion rates between steel inserts and polymer matrix, leading to modified insert geometries that accommodate thermal movement. Impact testing identifies optimal texturing patterns that enhance grip without creating stress rises that propagate cracks under repeated loading. The manufacturing process undergoes parallel optimization as production engineers refine injection molding parameters. Polymer flow characteristics dictate gate placement and cooling channel design. Cycle times balance productivity demands against dimensional accuracy requirements. Quality control protocols adapt traditional firearms inspection methods to polymer-specific characteristics, checking for sink marks, flow lines, and internal voids that could compromise structural integrity. Austrian military observers document performance data that contradicts their expectations. Glock prototypes function reliably after submersion in sand, mud, and water that jams conventional pistols. Temperature extremes that render steel-framed weapons inoperable barely affect the polymer construction. Impact loads that bend metal trigger guards leave the polymer frames undamaged and fully functional. Competitive manufacturers dismiss these results as irrelevant to real-world service conditions, arguing that laboratory testing cannot replicate the complex stresses of military use. Their objections reflect genuine concern about polymer durability, but also competitive pressure from a design that challenges fundamental industry assumptions. Traditional gun makers have invested heavily in steel forging, machining equipment, and skilled craftsmen, investments that Glock's manufacturing approach renders economically obsolete. Field trials with Austrian military units provide validation under actual service conditions. Personnel report reduced fatigue during extended carry periods due to weight savings. Maintenance requirements drop dramatically. The simplified mechanism rarely requires adjustment, and polymer construction eliminates corrosion concerns in humid environments. Most significantly, reliability statistics surpass those of existing service weapons across all measured parameters. The data accumulates into an irrefutable engineering argument. Polymer construction provides superior performance characteristics while dramatically reducing manufacturing costs. But acceptance requires overcoming psychological resistance to materials that appear insufficiently substantial for military applications. The Glock succeeds not by resembling traditional firearms, but by demonstrating that traditional materials choices serve convention rather than necessity. The decisive moment arrives not in dramatic testing, but through quiet, economic calculation. Austrian procurement officials analyze life cycle costs that extend beyond initial purchase price to include maintenance, replacement, and logistical support over decades of service life. Steel-framed pistols require periodic refinishing to prevent corrosion, replacement of worn components, and specialized tools for field maintenance. The Glock eliminates most of these requirements while providing superior reliability statistics. Production scaling reveals the economic implications that reshape military procurement thinking. Traditional pistol manufacturing requires skilled machinists, multiple machine operations, and extensive quality inspection to achieve acceptable tolerances. Glock frames emerge complete from injection molding presses every 90 seconds, cooled and ejected with dimensional accuracy that manual machining cannot match economically. Material costs drop by 60%. Labor costs fall even more dramatically. But the transformation extends beyond manufacturing into fundamental questions about what constitutes quality in military equipment. Traditional firearms culture associates excellence with weight, complexity, and hand-fitted components, characteristics that appeal to collectors but provide no tactical advantages. Military effectiveness demands reliability, consistency, and maintainability under adverse conditions. Polymer construction delivers these requirements while eliminating characteristics that serve aesthetic rather than functional purposes. International attention focuses on Austria as word spreads through military procurement networks about revolutionary pistol technology. NATO standardization requirements create pressure for member nations to adopt compatible equipment, but the Glock's performance advantages transcend political considerations. Law enforcement agencies become early adopters, drawn by weight savings and simplified maintenance protocols that reduce training requirements and operational costs. The psychological barrier proves more challenging than technical obstacles. Military personnel express skepticism about polymer weapons that appear toy-like compared to steel-framed service pistols. This resistance reflects cultural associations between weapon quality and substantial weight, assumptions that persist despite overwhelming evidence of polymer superiority in measurable performance characteristics. Glock addresses these concerns not through marketing, but through expanded testing that demonstrates polymer durability under extreme conditions. Prototypes function normally after being subjected to heavy vehicles, corrosive solutions, and impact loads that disable conventional weapons. Each demonstration chips away at preconceptions about materials engineering, revealing how traditional choices reflected manufacturing limitations rather than performance requirements. The engineering lesson transcends firearms design into broader questions about innovation versus tradition. Advanced materials combined with optimized manufacturing processes achieve performance improvements impossible through incremental refinement of existing approaches. But acceptance requires challenging assumptions that have governed entire industries for generations. A transformation that demands courage to abandon proven methods for untested possibilities. Within a decade, polymer frames become the standard for service pistols worldwide, validating Glock's engineering approach through widespread adoption across military, law enforcement, and civilian markets. The manufacturing techniques pioneered in Deutsche Wagram influence automotive, aerospace, and medical device industries, as engineers recognize that injection-molded structural components can replace machined metal parts across multiple applications. What began as a challenge to firearms tradition becomes a case study in materials engineering innovation. The resistance that initially greeted polymer construction dissipates as performance data accumulates across millions of service cycles. Organizations report reduced maintenance costs and improved reliability. Military units appreciate weight savings during extended operations. Manufacturers throughout the industry adopt polymer construction, validating Glock's fundamental insight that advanced materials could deliver superior performance characteristics while dramatically reducing production costs. Yet the deeper impact extends into design philosophy itself. The Glock demonstrates that questioning basic assumptions can reveal opportunities invisible to incremental improvement approaches. Traditional gunmakers focused on refining existing solutions, better steel, tighter tolerances, more sophisticated mechanisms. Glock succeeded by asking whether conventional materials choices served engineering necessity or merely industrial tradition. This paradigm shift influences thinking far beyond firearms manufacturing. Engineers across industries begin questioning whether their material choices reflect optimized performance or simply inherited practice. Automotive manufacturers adopt structural polymers for components traditionally made from metal. Aerospace applications embrace composite materials that provide superior strength-to-weight ratios. Medical devices utilize advanced plastics that offer biocompatibility impossible with metallic alternatives. The Austrian engineer's greatest achievement lies not in creating a successful product, but in demonstrating how systematic questioning of fundamental assumptions can reveal transformational opportunities. By approaching firearms design without preconceptions about appearance, materials, or manufacturing methods, Glock created solutions invisible to experts constrained by industry tradition. The test that reshaped an entire industry was not a single examination, but rather the systematic questioning of assumptions that had governed pistol design for nearly a century. Polymer construction succeeded because it addressed actual performance requirements rather than aesthetic preferences. Manufacturing optimization delivered superior quality through automated processes that eliminated human variability. Simplified mechanisms enhanced reliability by reducing failure modes. Today, the principles pioneered in Deutsche Wagram continue influencing engineering thinking across multiple disciplines. The lesson transcends any specific technology. Innovation often emerges not from refining existing approaches, but from questioning whether those approaches serve actual requirements or merely perpetuate historical limitations. In engineering, as in many fields, the greatest breakthroughs come from those willing to challenge what everyone knows to be true. If you enjoy calm, true stories about how engineering shaped the world, subscribe to the channel, leave a like, and tell us from which country you're watching.